Hello everyone and welcome to the third session from this video series, which is about developing electrical systems with Simscape. My name is Mohsen Alinejad and I'm a senior application engineer with a focus on power and energy fields at MathWorks. I'm based in Dallas, Texas. In this session, we're going to be looking in more details at the microgrid systems. Uh, this will be the continuation of my colleagues' work in the first session of this video series. So if you haven't watched Kristen's session yet, please pause this video, go back to the first session and start from there. So let me briefly talk about this session's agenda and what our today's end goal is. Mainly, I'm going to talk about the Simscape electrical essentials and how to develop a microgrid with a bunch of AC and DC power systems, including PV panels, AC generators, fuel cells, and battery. And also, I'll talk about the higher level power management unit and maximum power point tracking algorithm. So I'm gonna show you the final system that I'm walking you toward today. This is the system that we build up at the end of the day, and it includes a couple of AC generators connected in parallel, the AC/DC power converters, the DC system on the other side of the model that it includes the battery and a couple of fuel cells and also PV array. The first thing we are going to do is look at some of the key components and how they operate. So we want to incrementally build component details and evaluate operation and satisfy ourselves that we are seeing exactly the behavior we expect for a given component. And we are going to look at a couple of components in here. We are going to begin with impedance matching and maximum power point tracking, MPPT. That's going to influence our PV cell, PV arrays, solar panel. So let's open up this model in here. I have the first model, impedance matching, and I have two subsystems in here. I'm going to expand them by using the space bar. So on the top, we have this changing load and a fixed source. We ramp up the voltage of the load. We don't have a fancy system in the system one. System two, we have a buck boost converter with maximum power point tracking. If you open this maximum power point tracking, we have a detailed control. I'm going to run this system now. We're going to take a look at the details later. So if I open up the data, simulation data inspector, SDI, we can take a look at the load voltages for the top system. The source voltage, you can see the load voltage increasing and the source voltage decreasing in here. And we can watch the power. The power increases up to the maximum power point and then decreases. You know, here the maximum power it's around 100 watts, which occurs at 100 volts for both voltages of the load and source. So we have an impedance match in here. So I'm going to uncheck these three and take a look at the second subsystem with the buck boost converter and maximum power point tracking. So if we take a look at the load voltage increases, the source voltage, it has a transient, it goes to 100 volts and it stays there. It sets around 100 volts. The 100 volts is where we had the maximum power point. And if we look at the power tracks up to 100 volts and it stays at that point. What's happening is that we are dynamically changing the impedance that the source is saying to keep it matched regardless of what's happening on the load side. So it's doing that, and it's doing that by changing the duty cycle. So let's take a look at the duty cycle in the maximum power point tracking algorithm in here. This is a so-called perturb and observe MPPT, maximum power point tracking. If we take a look at the rate of the change of the power, that's really dependent of the rate of change of this duty cycle. We have the increment value in here. Now it's 1.5 e minus 3. If I double click on that, open it, and change the value to a larger amount, like 1e minus 2, for example, then if I run the system with this value, 1 in e minus 2, I'm gonna run this again to see the difference. So now I'm gonna go back to the data inspector, and you see now it's a little bit noisier because of that bigger step. And certainly we see it in the source voltage. But still, we are tracking the maximum power point with higher fluctuations, with bigger jiggles. So that's the first part of testing our system with the maximum power point of a voltage source. Now it's time to go and check a real life example in here. The next example, which I said it's a real life example of impedance matching, is maximum power point tracking of a solar panel instead of having a fixed voltage source. So in a real world application, we have a detailed PV solar cell, which you can see it in here. And if I double click on that, you can see it's a pre-parameterized power cell with a manufacturer part. You can definitely change that manufacturer power part to another thing that you use in your system. And we have these cell characteristics parameterized in here, so you can easily change the values for them. And we have this profile of the irradiance, which we are simply ramping up to 1 kilowatt over meter squared and ramping it down to 0. We are using a Simulink to physical signal converter to get Simulink signals to the Simscape data. And we have this maximum power point tracking. It's unchanged from the previous example. We have ideal DC to AC system in here. So it's a single phase inverter. And what we are doing in here is very basic. We are measuring the energy from the DC side, and we transfer it from DC side to the AC side with using this Simulink model, Simulink approach in between, in the gap. So because we have interconnected two networks, the AC side and DC side and AC side, we have two solver profilers, and that lets us to set two different step times, sample times TS underscore DC, and on the other side, the AC side, TS underscore AC. So typically the AC step size is larger, depends on your system, but you have the flexibility to change it based on your demands and requirements. And in here, you can see the TS underscore AC is 2e minus 4, and TS underscore DC is 1e minus 3. So two separate step times, sample times for each network. And this brings efficiency to our Simulink model to optimize based on the different characteristics that our networks have. So the other thing is this, we have written this MATLAB script. So, it's a way of showing the power profile to visually confirm the different power waveforms, the curves for each irradiance. And if I run this, you should see a figure upright in our live live script. I'm going to minimize the Simulink model so you can see this figure. The power curves of solar cell regarding the irradiance is shown in blue. The red curve is the maximum power point track that, you know, our system is not aware of. It doesn't have any knowledge on the blue waveforms, but because it's tracking the maximum power point by perturb and observation, it's going, it's tracking the maximum power. It's simply looking to define those peaks by regarding those changes that it sees in our system. So it's a nice way of visualizing, by using MATLAB graphics. It gives us these nice features to verify and see the operational behavior of our power system. So I'm going to close this down and scroll down in here to go to the third example that we have in here. I'm going to close the previous model and open up the power sharing. We want to test the power sharing on AC generators. We want to look at the traditional mechanism of the power sharing, which is called frequency droop, which is for active power. So this is, as I mentioned, for active power sharing. For reactive power sharing, we have the voltage droop for AC salt, but we're not going to cover that part for the sake of time. But you still have the feature to control the reactive power. We want to focus on the active power in this presentation. So on the control perspective, we have this speed controller in here for the generator. We want to regulate the frequency and speed, but the droop, which is an auxiliary signal measuring the active power, multiplying it by a drop value. And what that it does is it creates this droop curve, which it goes from zero loading to full load, 1 per unit. Well, the per unit is the normalized value based on the rating of the machine. And we can see it drops 5% based on that droop value we had in the auxiliary branch. And if we load the system 0.5 per unit or 50% of the system, we would end up to see that dashed line where it sees that blue constant value. But what it means is that the power sharing is working, and we can take a look at that by opening this example in here. So it's going to open up model C, the third example. In this example, we're going to be testing the power sharing between two generators which are connected in parallel. In generator 1, if we go underneath, we see 5 megavolt ampere for the diesel generator. We have the AVR and exciter and the governor control. We see the droop control in here. If we go back to the main page, we see active power load and reactive power load. We can change it with this variable active resistance. We have the active power reference in here, which is 4 megawatts. It's 80% of the nominal value rating, and that's for one of the generators. So we're just gonna test the active power. For the reactive power, we implemented that. We use the variable inductors. We can set a reactive power value, but in here we use the very small values, so you can change that when you're playing with these models. But for this one, we are gonna keep it as is. And yep, as I mentioned, these are two parallel generator connected, and we're gonna make sure the voltage, the frequency droop for power sharing is working correctly. So here we have droop P1 and P2 equal to 5%, 0.05. And when we run the system and we take a look at the frequency droop on the left side, we have this blue curve for both of them, but for the voltage droop on the right side, we don't do anything with that, so it's not working at the moment. So you can see G1 and G2, the powers from generator 1 and generator 2, they're equal and stay at the same frequency. It's off the line a little bit, and that's because we have this. The blue line is steady state line, and it's a dynamic system. So the steady state condition and the transient behavior, it's a little bit different, but they generate exactly equal powers and they stay at the same frequency. It means they share power with the equal shares, equal power sharing when the droops are the same. So now let's make a change to the droop P2. And for this second generation, we set it half of the previous value, 2.5%. Of the droop P1, and let's stop the system, rerun it again to make sure that the voltage, the frequency droop for power sharing is working fine. So if we go back to the live script, now we see we have two different droop curves. For the red one, for 45%, and for the blue one, the 2.5%. They are at the same frequency, but the power shares are different. And in fact, generator 2, which has twice the power of the generator 1, it has the value for droop half of the other generator. Twice the power, half the value of the droop. That's the fundamental of the frequency droop power sharing, and we verified that by using Simscape, and we are seeing that on the live script. So now I'm gonna close down this model, stop the model. So we have confirmed this solar array and maximum power point tracking. We confirmed the power sharing for frequency droop, and the final test is gonna be the power converter. I'm gonna open up the model D, which we have a simplified test harness, ideal three-phase AC system, source and sink voltage. On the DC side, we have source and sink on the DC side, ideal DC source, and it's going to be a bi-directional system. We have the power converter in between. In here, if you look under that system, we have two separate networks by using Simulink, interconnected networks like the previous example, but a little bit more complicated than the previous one. In this example, we work on active and reactive power by using the DQ reference to transfer the power across the boundaries of the AC and DC system. Because we have Simulink in the middle in the gap, we are able to split these two systems and have different time steps. We're gonna have 1 megawatt for active power and 800 kilowatt for reactive power. I'm gonna run the system here, take a look at the system response, and make sure that the system is working to confirm the connected operation of both systems. So going to the Simulink data inspector in here, checking the reactive of the active power of the AC and active power of the DC. They should be overlaid, and they are overlaid. And as you can see, we are tracking 1 megawatt, and in between 5 and 6 seconds, we have a drop to the power. That's because of ramping up the reactive power. Reactive power is ramping up, so that's the expected behavior. So we confirm the operation of the system as well, and we cannot go through all every single components that we have in the system, but we looked inside the main components. Now it's time to move over and go to the other parts of the system, like verifying the battery management systems, the battery management, and the fuel cells. Now I want to start talking about the fuel cell system. So we go to the directory tree a underscore ac underscore dc system. We're gonna open up this system, this model in here. Uh, so while it's opening, maybe we can talk about. So let me minimize this system in here. I wanna talk about the fuel cell on this live script. So what you see in here, the fuel cells, we have got two of those fuel cells in our system, and we model them with this lookup table. So we have polarization curve on the right side in here. So, and what we do is we have this polarization curve, current versus voltage. So we measure the current, we input it to the lookup table, we calculate the voltage, we feed it through the controlled voltage source that we can, make a model, a system level. Let's say that's an average model for a fuel cell. It's not a detailed fuel cell model. We can do that, of course, in Simscape, but it's going to take longer times for simulations. So we keep it as average model. So if we run this code in here, it plots the fuel cell polarization curve, and you can see the relationship for this particular fuel cell between the voltage and current. And depending on what your fuel cell is, you can generate these lookup tables, either getting from the fuel cell suppliers, or you can generate lookup tables by detailed simulations. So by saying that, now we can bring back the Simulink model and talk about the components in here. So uh, we are we have already seen the AC generators and the power sharing between them, AC to DC power converters, PV arrays, the fuel cell. We just have seen that in the live script. Now it's time to talk about the battery. For the battery, we use a pre-built battery model from the Simscape electrical. It's suitably parameterized for us, so you can see all the characteristics that are important. So you can save it in the workspace. You can double click on that and check the values if you want. And so we want to start looking at the operation of this particular system and make sure that this power management system, the power transfer management, make sure that it's working appropriately and all the components are doing as they're supposed to. So we put together this high-level power management uh, system, and we focus on the key elements in here. So the main element in here is this, AC load limit, 8 megawatts. When it's greater than 8 megawatts, the DC power starts supplying and helping the AC system. So AC limit is 8 megawatts. We shouldn't generate more than that nominal values of the combined two generators. So we have the power transfer limit across the AC to DC limit is 1.5 megawatts, and the combined power for the fuel cell and PV, it's a limit of 500 kilowatts. So if that hits 500 kilowatts, we start using the battery. That what's basically these numbers means. So these go-to tags, if we just click on that, we'll see there are some hyperlinks in here. So if we click on that, it brings us to the corresponding control unit. For example, this one is the battery converter, uh, which is controlling the battery power based on the values is set in the power transfer management unit. And similarly here, AC reference, if you double click on that, it takes us to the AC reference for the ideal AC to DC power conversion. So now let's memorize some of those numbers. A megawatt limit for AC load limit before the DC power kicks in. We transfer all the PV power. And if we go above 500 kilowatts, we'll start using the battery above the limit of 1.5 megawatts of the power limit. Let's simulate this system and see how it looks in practice. We have a 2-minute window for the simulation, and you see when it starts running, you see it's faster than real time. It's so much faster than real time. For the 2 minutes, it's gonna simulate the whole system in less than, like, I don't know, 30 seconds. Something like that. Now let's go to the data inspector, and the first thing I'm gonna look at is the load profile, the AC underscore system P underscore load. So I'm gonna maximize the window, and you see the loading here on the AC side. So it has two peaks, a little bit about above 12 megawatts here and 9 megawatts on the first one. Next thing I want to look at is the power generated from two of those AC generators, AC system P Gen 1 and AC system P Gen 2, the power from the system number 2, generator number 2. The generator 2 providing twice the power of the generator 1 as the droops. Let me close this down. The droops in here, you see P2 is half of the droop P1, so that means generator 2 generates double the amount of power of generator 1. So now I'm gonna see the total power of the AC system in here. P underscore gen TOT, two generators combined, it stays at that limit, 8 megawatts as we want. So the management limits, there is some limiting in here, but at some point it breaks out. The generator is not staying at 8 megawatts. That's problematic. So because it's passing the rating. Are we seeing what we expect? Is this a simulation problem or a control problem? Now I'm going to uncheck this to investigate this scenario. What's going on in here? The AC to DC power transfer, I'm going to check that one. AC, DC, PAC power transfer. I'm going to check that one as well. So let's look what's happening. We transfer the power to, where the peak meets. So this is a successful operation. When it hits the limit, we start transferring. But when will the second peak, we have a limit of 1.5 megawatts, so we cannot provide more than that. So that's why the generator have to pick up the extra and generate over that rating value. So that means the simulation is working correctly. Our system, our power management unit is not meeting the demands for here. So I'm gonna check all these boxes for the fuel cell powers, PV power. The PV power is really low in here comparing to the other powers. Uh, so the battery is kicking in when the fuel cell and PV hour hits 500 kilowatts. The battery is kicking in, and there's a limit of the power of the battery. So the power transfer limit is 1.5. So we are limiting the battery power. So we are seeing the correct behavior, but for meeting the demands, we need to make some changes because the PV power is very small in here. I want to go inside the PV array, double click on the uh, uh, solar cell with parameterized configuration and change the number of parallel connected strings from 1 to 10. And Now I want to run the system again and resimulate it and see how the system responds this time. By simulating this again, we'll see how that impacts the power sharing, the overall power sharing, in the entire system. I'm gonna close this down in here. And now if I maximize the window in here, you'll see the value for the power PV array power. It is indeed multiplied by 10, around 300 kilowatts, but we reduced the fuel cell power. The combined power was 500 kilowatts. So that means, we're using the battery, but the power management system, we need to go there and change some values, increase the value of the combination power first. So, but before doing that, let me go back to the live script in here. Let me close this data inspector. So I'm gonna scroll down to the values that we want to change them. So in here, the combined power from fuel cell and PV, we need to change it to 1 megawatt. And the 1.5, we want to make it 5. So I'm going to double click on that. 5e in power of 6. And that 500 kilowatts, I'm going to double click on that and change it to 1 megawatt. So let's rerun the system again and take a look at the data inspector as soon as it comes back. Let's maximize this window. We're seeing the components of the DC system. The fuel cell total has been improved. Minimize the usage of the battery in this side, but we are not limiting that, so we are meeting that peak because of the changes that we made previously. So the value for the power of the battery is a little bit high, so that might not be what you want to do, or maybe it's what you want. So uh, this is simulation. You can investigate it. You can see if that's what you want, or no, you want to change some other things to make it a better simulation. That's the beauty of the simulation, right? So now let's go to the AC system. Look at the power, load power, the AC, the total power of the generator. So we indeed limited that to 8 megawatts, and for the entire time it is uh, equal or less than 8 megawatts. So this is the entire simulation. The question is that what you want, or the simulation is not working as your engineering designs are required? So this concludes the third session of this video series. We talked about Simscape electrical essentials. We used Simscape to build confidence in the development and test of interconnected AC and DC system simulations modeled by incremental creation, test, and integration of components covering a range of fidelity levels. Simscape provides a platform upon which more detailed system simulation can be created. I hope you find this session useful, and thank you for your attention.